Good morning, ladies and gentlemen. My name is Alicja and I am from Silesian University of Technology in Gliwice in Poland. And today I will present my research on Femme analysis of wooden joints and wooden structures of the electric car's frame. Wood as a construction material has been known to man since ancient times. Over the centuries, it has played a significant role in architecture. Nowadays, wooden structures, especially in construction and furniture, are revived due to such trends as ecology, care for environment, and the desire to be closer to nature. The finite element method, or Femme for short, has played a significant role in testing the strength of materials for over 40 years. It's a numerical method that, together with the proliferation of computers, caused a real revolution in the field of strength calculations. The first stage of the research was the Femme analysis of individual wooden joints. Three materials were analyzed for each joint: oak, pine, and plywood. Oak wood and pine wood have been modeled as orthotropic materials due to the different properties of the wood along and across the grain. The plywood has been modeled as an isotropic material which has the same properties in all directions. The first step was to analyze the screw joint. In this case, only half of the geometry was modeled and the plane of symmetry was used. Two types of contacts were used to connect two boards to each other: frictional contact between contacting surfaces, kinetic friction coefficient of 0.2, and the MPC element to represent the geometry and the connection between the surface of the whole. The behavior of the MPC element has been defined as perfectly rigid. Among the parameters of the MPC element, there is a so-called pinball region, which is marked in the left picture with the red ball. This area represents the screw head that also interacts with the surface. In each tested material, the highest stresses occurred in the same place, which can be seen in the right picture. These stresses are generated indirectly by the action of the screw head pressing the material of the wood board. A glued joint has a different characteristics than a friction joint or a screw joint. There is no weakening of the material by breaking its homogeneity. Properties of the joint itself, not only of the glued material, play an important role. There are several methods of modeling adhesive joints. One of them is the actual modeling of thin layer with a given material properties. However, due to the size of the elements, this method is computationally time-consuming. The second method that was used in this Femme analysis is to model the joint as a cohesive joint and cohesive zone modeling. The connection of element was ensured by adopting the interaction in the form of cohesive contact. The properties of the cohesive zone material are shown in the right picture. The next step was to establish contact between elements. For this purpose, the type of bonded contact was adopted, and then the fractured contact debonding element was added, which is responsible for the cohesive connection of the tested joints. These parameters allow to determine the force needed to break the connection. The joint was fixed at both ends, and the force was applied perpendicular to the joint so that it would break. Next part of the research was the Femme analysis of the wooden structure, the car frame of the Silesian Green Power team. The structure of the car's frame should ensure stiffness while driving, even distribution of fail through the arrangement of batteries and motor, and meet the safety requirements of the competition regulations. The safety elements are the front plate, to which is a foam with a specific compressibility attached, which should suppress the frontal impact, the front roll bar above the driver's legs, and the rear roll bar, which are to protect the driver in the event of possible fall and overturn of the vehicle. The car frame geometry has been simplified to reduce computation time. Half of the model was used for calculations and the symmetry condition was assumed. The connections of elements were ensured by adopting interaction in the form of cohesive contacts. Next step was to determine boundary condition and applied loads. The frame is fixed at the ends of the shafts. All forces are resulting from half of the assumed masses, because only half of the structure was tested. The material used for the frame is plywood and for the shaft structural steel. The greatest stresses were noted in the place where the element was supported, at the end of the shafts. The maximum stress was 87.4 megapascals and took place at the end of the front shaft. Increased stresses were also noted in the area of the driver's seat. There, the stresses fluctuated up to 14 megapascals. Despite the value, the stress distribution at this point was even. The area of the increased stress was also the area of the rear shaft mounting, which can be seen in the picture. At the end of the shaft, the stress have risen to 16 megapascals. The stresses resulting from the connection of the shaft with the frame were approximately 3 to 4 megapascals, while the stresses in the plate under the motor were approximately 5 megapascals. In the last stage of the analysis, the stresses and displacements experienced by the frame during driving in a turn were examined, the influence of the centrifugal force and the aerodynamic drag. During the race, the speed achieved by the car is approximately 17 meters per second. The chosen corner was the Lafayette corner at the Silverstone track. The radius of this turn is approximately 60 meters. It's one of the most difficult corners a driver has to deal with among the tracks where the team starts. Having the above information and knowing the weight of the car with the driver, which is about 103 kilograms, it's possible to calculate the centrifugal force acting on the car in a turn using the given formula. The calculated centrifugal force was 496 newtons. A point has been created which represents the center of gravity of the entire car. To this point, the centrifugal force was applied, and then the center of the gravity was connected by MPC elements to the centers of gravity of the individual masses, the driver, batteries, and motor, as it can be seen in the right picture. The force resulting from the aerodynamic drag, which is approximately 9 newtons, was evenly distributed at the points of attachment of the bodywork to the frame. As a result of the Femme analysis, the total displacement in the frame was 1.65 mm and took place at the top of the frame of the left battery. The displacement in the vicinity of the driver's seat ranged from 0.8 to 1.13 mm. The displacement near the plate under the motor was 0.6 to 1.24 mm. So to conclude, due to its hardness, oak wood is characterized by a significantly lower displacement as a result of the load than other tested materials, 2.5 times less compared to pine wood and 3 times less than a plywood. For a glued joint, the stresses obtained are very similar for each material. The differences are below 1%, so they result from the joint characteristics and the material of the joint, not the type of wood which has been connected. For the screw joint, the stresses for oak wood are twice as high as for pine wood and plywood. This is due to the high rigidity of oak wood. The design of the frame was done correctly, as the car frame is not subject to stresses exceeding the allowable stresses of the material, both under static load and when driving in a turn as a result of centrifugal force. Thank you for your attention. Do you have any questions?